It's my great honor and pleasure to introduce Professor Paola Cappellaro from MIT. Professor Cappellaro is the fourth professor of engineering at MIT. She is a professor of nuclear science and engineering, a professor of physics, and a member of research lab for electronics, where she leads the quantum engineering group. Professor Cappellaro received her Ph.D. from MIT and then joined Harvard University as a postdoctoral associate in the Institute for Theoretical Atomic, Molecular, and Optical Physics before going back to MIT as a faculty. Okay, please join me to welcome Professor.
Thank you. And Friedman, you should stop your sharing, otherwise I cannot start mine. Thank you. Very good. Okay. Can you hear me and see my slides?
Yes, thank you.
Perfect. Thank you very much for the invitation to present, and also for the very nice scheduling, which helped me just after Friedman's presentation, because I'm sort of hopefully continuing on the same topics and with somehow a complementary view, if you want, in which I'm really trying to sort of tease out what is quantum in quantum sensing, if you want, and why we want to do quantum sensing, and what type of advantage we can have over a classical sensor when we are exploiting quantum properties. And so the first message that I really want to convey is, why are we interested in using quantum system for sensing? And this sort of goes back to the very old thought experiment of Schrödinger, the famous Schrödinger cat, that can be either awake or sleeping inside the box, and we don't know what it's doing until we open the box. But really, when we look at a real experiment, well, we can really a superposition of a quantum cat, or of, if you want, a macroscopic cat. And that is because the cat, even inside the box, is still interacting with its environment. Any molecule of air, any photons inside the box will perturb it and immediately collapse it into either being awake or sleeping. And this is because quantum systems are fragile, because they interact very strongly with the external perturbation. And this is probably bad if you're trying to make a quantum computer, because you would like to keep this a very large superposition, but they also make for very good sensor. This high sensitivity to any external field and external perturbation makes quantum system very good quantum sensor. And of course, the goal that we have is to reach sensitivity, which can be beyond what is possible with classical sensor. And this is a form of quantum advantage, which sort of mimics the advantage that you have in quantum computers. So in quantum computer, you have an exponential advantage. For typical quantum sensor, I mean, there are many flavoring, but the most typical scaling that we have is that if you use quantum systems as a classical sensor, or we just have n classical sensor, the signal-to-noise ratio improves as a square root of the number of sensors themselves. However, if we use quantum sensor by exploiting their most fundamental property, in particular entanglement, we can have a scaling with the number of sensors, which is proportional to n. And so this gives this, so if you want, polynomial improvement with respect to classical systems, which is what gives the quantum advantage. However, reaching this quantum advantage is relatively difficult. And so when we were working actually together with Friedman and also Christian Degen in trying to analyze and provide a review of what we mean by quantum sensing, we came up with, if you want, the 3 classes of quantum sensors. So the first one is where we just use a quantum object to sense things. So if we're considering, since we were just discussing a few minutes ago, MRI, of course, we're using spins in order to detect, for example, the anatomy of brain, and spins are intrinsically a quantum object, but we can describe them really as classical magnetic dipoles. So we don't really use the whole, if you want, quantum mechanics to describe very basics MRI experiment. So we are using quantum object, but not really exploiting their quantum property. And this is a sort of, if you want, a quantum 1.0 type of technology, which we are not really so interested in defining, at least not today for me. So what we are really interested, or what we really mean when we define a quantum sensor, are cases in which we are using, for example, at least some quantum property, for example, coherence and superposition, in order to have better sensitivity. And even more, what we would like to do, as I said, is to use entanglement in order to achieve this quantum advantage. And of course, there has been already some demonstration of this type of sensors. So we heard a lot about these NV centers. So if you use a single NV, or if you use an ensemble, but we want to use in, if you want correlation among the spins, these will fall into this category. Another good example are atomic clocks. So atomic clock are sort of like in between. Sometimes people complain to me that they should be in the first category, but really we had a lot of advances, for example, brought by Julie and Anna Maria Ray, in which you're using quantum logic to improve your ions and atomic clocks. You're using ensemble and correlation to make them even better. So it's sort of like bridging that gap to achieve these really exploiting quantum properties. And even LIGO in its first instantiation was, if you want, in the second category, like just an interferometer. But more recently, they've been using squeeze light, injecting squeeze light in order to improve the detection of gravitational waves. So we already have these examples of achieving quantum advantage with this type of systems. And really, this is the type of things that we are also trying to do to improve quantum sensing, and really to bring the advantages of quantum sensing to real applications. Same as Friedman, my favorite quantum sensor is the NV Center in Diamond. And I think that, like, after this talk, I don't need to really motivate why this system is awesome. It can really sort of bridge a lot of different modality of sensing and different applications. So looking, for example, at magnetism at the nanoscale, looking at effects from superconductors, effects from ferromagnetic materials, but with a spatial resolution, which are really down to the nanoscale, for example, through this scanning tip. It can look at biological effects, for example, some work done to detect HIV RNA in like a bioassay type of setup. And also it can look at just the dynamics of other quantum systems, for example, correlation of quantum spin associated either with the diamond or on the surface of the diamond themselves. So it's really a very powerful sensor with many different applications. And well, my next slide probably it's a bit superfluous, since we already had an introduction on NV Center, much better than mine. And by now I keep it really down to just one slide. Again, these are just optically active defect. So we will illuminate with green light and we see the red light emitted. And to put in a plug for Thorlabs, which was the 2 talks ago, they actually sell quantum diamonds with NV defect. So you can also purchase that and start doing your own experiments. And of course, we combine typically with optical polarization. So if you want cool down via optical means, and I use the conventional optical readout for NV centers, and we combine that with microwave control, where of course your NV center acts a little bit like the compass needle, pointing up or down in response to an external magnetic field, and you can have magnetic resonant driving ODMV, and where you detect a lot of light if it's pointing up, and less light when it's pointing down, and you can drive this very nice coherent superposition. And this is work going back to 2006 by Lilich. But people have been observing even better coherence time since that time. So how can we achieve this type of quantum advantage with this type of defects? One way that indeed we propose even back then in some of the first few proposals is to use large ensembles of NV centers and trying to exploit the interaction among them. However, the first thing that appears when you're having large ensembles with very, very dense NV center is that the interaction among the spin themselves sort of make your coherence time decrease. And so you have less time to do the detection. And so the sensitivity, so if you want the minimum field that you can detect, is not so good. And you cannot go for very long sensing time because the coherence kicks in and you lose your signal. So what you can try to do is to try to, if you want, decouple or cancel out this interaction. And some very clever people in Michel Looking group, they devised very powerful sequences which were able to improve dramatically how well you can detect your magnetic field with this very high dense system. However, this does not give you yet, if you want, the quantum advantage per se. So if you were able to change the number of NVs inside the sample, which like in this experiment we were not doing, you would see that the sensitivity would just improve as the one with the square root of the number of sensors at most. However, if we could indeed exploit instead interaction among the spin and achieve a type of correlation, for example, in the form of a squeeze state of the spin, then the sensitivity could improve even more. We proposed that back in 2009, and we have not really been able to demonstrate an advantage. We have been able to demonstrate a small advantage based on some small entanglement, but this powerful scaling with this, which improves over the classical level as a square root of n, has not been able to demonstrate yet. So of course, I've been trying to do something else in between. And the idea is that, well, maybe there is something in between these two limits. So we might not just use coherence of single spin, and we might not look for the full entanglement enhanced metrology, but there is maybe some regime in between the two where we use some small quantum system, some small amount of entanglement to achieve some task that a single qubit sensor, a single quantum sensor could not achieve. And this is like a very fruitful regime, which sort of is at the intersection where engineering advances come together with the fundamental quantum mechanical advances to bring some real practical application. And this is what I want to talk in the rest of my talk. And there are many different things that we have looked over the years. For example, one can use some additional qubit sensor to do quantum error correction, or to use them as quantum memory in order to both improve the sensing time and so the coherence time, or to look at correlation. What I'm going to focus today is how to use some additional control and some additional level, either some virtual degrees of freedom or some real degrees of freedom associated with our spin in the system in order to achieve frequency up conversion, in order to achieve vector sensing, and also to enhance coherence. So the first thing that I want to talk is this vectorial sensing, which is achieved by doing some modulated driving. So before that, I want just to step back and sort of describe some very simple way in which you could do vectorial sensing. So first of all, you could do the typical Ramsey magnetometry to detect fields which are in the z direction, if you want, aligned with the NV axis, with the NV quantization axis. The idea here is to prepare superposition state of your NV center, let it evolve for some time under an external magnetic field, which is aligned in the Z direction, and then detect out the phase which has been accumulated, and this will tell you how strong of a magnetic field it was there. If you want to instead detect a transverse field, if you do this, you get some perturbation, but it's very small, so it's a very insensitive way of detecting transverse field. So what you can instead do is to detect fields which are rapidly oscillating at the resonance frequency of your spin, of your NV center, and this will indeed induce a precession of the spin now in the let's say, ZY plane. But this can only detect things which are oscillating at the resonance frequency of the NV center itself. So these are gigahertz. For the Z field, you could indeed also measure oscillating field, okay, for example, by using dynamical decoupling sequences, but the typical frequency here are on the order of megahertz, while here on the order of gigahertz. So it's difficult to bridge between these two modalities, and also the experiments are quite different. So if you have systematics, if you have experimental error, they will be different in the two experiments, and so it's a bit difficult to really get out some very nicely consistent way of detecting spin. So how can we bridge these two and find a single protocol to do indeed vector magnetometry? So before I explain that, I just want to take a little bit an aside. So if you do want to do this Rabi magnetometry, how can we understand that? Well, we could have this oscillating field, as I said, like a transverse field that we might want to measure or use to control the spin. If you have this oscillating field, you can always consider it as the sum of two counter-propagating field. And then if you jump into the frame rotating with the red field, this will become, of course, static in that rotating frame, and the other field will be rotating very fast. So we can actually ignore it. The static field will then cause a tipping of your spin, and you can detect how fast it is indeed rotating, and with that, you do Rabi magnetometry. Indeed, we did that actually with my colleague Daniel Breger of Lincoln Lab, and achieve some very good picotesla level sensitivity for this fast oscillating field by using their expertise in achieving the best overall sensitivity in ensemble, like large ensemble magnetometry. So this is the current sensitivity limit, if you want, for this high frequency field detection. Now, going back to our oscillating field, if the oscillating field is along the Z direction, and again, you jump into a rotating frame in the XY direction, well, okay, nothing really happens. So it's a bit boring, but we can use this fact to achieve this vector magnetometry. Let's say that now I have an oscillating field, okay, which is in some arbitrary direction in the in any direction in the Z, XY space. And in the lab frame, this is at this frequency omega s. But if I look at it in the rotating frame, rotating at the frequency of my applied microwave, for example, then this splits the two components. So the component which is longitudinal will stay at its original frequency, but the one which is in the transverse plane will have a shifted frequency by the rotating frame frequency itself, omega. And so one can sort of detect the two in two different ways. And indeed, this is what we do. We detect the transverse component by applying, for example, by looking at this shifted frequency, while we detect the longitudinal component at the original frequency. And we can indeed see them. In this particular case, we see that we were applying a field at about 28 megahertz, and this can be detected, the longitudinal component can be detected at the original frequency, while the transverse one is shifted by the NV frequency. And so we are able to use basically the same setup, the same NV, and the same experimental sequence to detect two components of the magnetic field, so the X component and the Z component. The limitation here was that, as you can see, the difference between the two is only about 6 megahertz. And this was what the frequency of the MV we needed to set. And that, if you know the technicality, that means that you need to work at a very specific external magnetic field. And this is, if you want, the constraint that you have in order to be able to detect both of them simultaneously. If we make this field frequency, the signal frequency much higher, then it's not really possible to also detect the transverse component with the same type of sequence. And so this is sort of a bit of a limitation. But the advantage is that you had the same experimental errors, and you can use a single MV to do both vectorial magnetometry with all different axes. And so you can also, of course, apply this to an ensemble without needing to use different classes of MV for different directions. So to avoid this sort of bandwidth limitation that we had in this sample, we decide to use the MV center as a quantum frequency mixer. So what you would need is, of course, sort of like to up-convert or down-convert your frequency to a frequency which your MV is particularly sensitive to. And this was what we wanted indeed to do. So again, like if I have just an arbitrary field which is oscillating, I have that they are sort of like split. The two components are split, and one is has a frequency shift. But this frequency shift might not be at the frequency target which I like. And so what we can do is to add some additional bias field at an intermediate frequency, so that I will have an effective signal, which is now nicely situated at a frequency typically on the order of tens of megahertz, which my MV can detect very easily with common detection protocols that people have sort of like employed them many times. And indeed, we do this, and now we are able to detect, for example, signals which are at around 150 megahertz, which is typically frequency difficult for the MV center, but just using very simple protocols. So how does this work? Well, we can analyze this by using Floquet formalism, which what it tells us that really what is happening is that we are creating some additional virtual degrees of freedom, some additional energy levels, thanks to the drive. So thanks to the drive of our bias field in addition to the signal field. So we are engineering some additional degrees of freedom, which allows us to do this better sensing task. And the advantage, again, is that we can then use a typical Rabi or CPMG sensing sequence to detect fields which otherwise we will not at the gigahertz that we will have needed for Rabi or low megahertz that we would have needed for CPMG. The disadvantage is that we have a hit in the sensitivity, but of course, if you cannot sense this sort of like 100 of megahertz or maybe 100 of gigahertz frequency in other ways, well, you can sort of survive to this reduction in sensitivity. So we demonstrated that, and we demonstrated that we can achieve the same level of sensitivity whether we use a Rabi sensing protocol or a CPMG sensing protocol. CPMG is where you apply periodic pi pulses which match the frequency of your target signal. And we can indeed achieve very good sensitivity with this protocol. So this is an example in which we just use control to engineer, if you want, this fictitious additional energy level. But what we can also do is actually to use additional degrees of freedom inside the diamond, in particular associated with the nuclear spin, in order to improve the sensing task, and actually use the electronic spin now just as a controller. So before I introduce the NV Center, and also I think that in the freedom introduction, we focus on the electronic spin. But of course, we also have a nuclear spin, in particular, the nitrogen-14 nuclear spin, which is a spin 1. And this has both an hyperfine interaction, which couples the nuclear spin to the NV, and also a quadrupolar interaction, which gives, if you want, a local magnetic field on the nuclear spin itself. And we can control also the nuclear spin in the same way that we do the electronic spin, and again, by mapping the nuclear spin state to the NV center, also read it out. So this is a much slower this is I think, Rabi oscillation, it's better labeled, of the NV center, of the nitrogen-14 of the NV center. So we can, in principle, also use this as a magnetic field sensor, but it's not very sensitive. And so what people have been using the nitrogen spin is for this idea of building a nuclear spin gyroscope associated with the NV centers, because nuclear spin are as sensitive as electronic spin to rotation, and we can use the electronic spin to mediate the polarization without a control. So we indeed were looking at the nitrogen-14, and we wanted to test the fact that nuclear spin, in principle, should be very, very robust to any external perturbation, and so have very long coherence time. Instead, we found relatively long coherence time. This is almost millisecond time, but also some puzzling behavior. In particular, if the NV center is in the -1 state or +1 state, the coherence time was much shorter, on the order of 0.2 milliseconds instead of almost 1 millisecond. So what we figured out very quickly is that actually variation in the hyperfine and quadrupolar interaction were reducing the coherence time. So one can sort of use some econ on the NV center to correct for this. But we were also interested in trying to find some other system which hopefully didn't have this problem at all. And so what we did was to turn to N15. So N15 is a spin 1/2 isotope, so it does not have any quadrupolar interaction. So well, it should have better coherence time. And there is no hyperfine if the NV is in the MS equals 0 state, where the spin is indeed 0. And so what we expected was that as we were going from the -1 state for the NV center and looking at the coherence time of the nuclear spin, so if we move to the MS equals 0, we should expect much longer coherence time. Instead, it was a bit longer, but not as much as we were expecting. So again, this was a brief puzzle until we, of course, figure out, see if I have some water, I don't have water. We figure out that actually there is some hyperfine, because we have some transverse component to the hyperfine, and as soon as you have a little bit of external transverse magnetic field, this is coupled in a very, very effective way. Because the I need to find water, otherwise I'm not going to be able to continue here. One sec. Sorry about that. Let's see if it is better. Maybe not. So what we found was that transverse field coupled into the hyperfine, giving rise to a shift in the resonance frequency. And if the hyperfine is inhomogeneous, then you have again some decay. And this shift can be quite large, especially around the level anti-crossing for the nuclear spin and of the electronic and nuclear spin. So what can we do? Well, again, it becomes better actually to sort of alternate between the -1 and +1 states of the electronic spin. And this will actually improve the coherence time of the nuclear spin itself, because this will sort of refocus the hyperfine inhomogeneities that we otherwise observe. And indeed, if you look again at the nuclear spin coherence time, by doing this protection scheme, we can improve the coherence time by almost an order of magnitude. So the last thing that I want to say is that we can actually use the electronic spin also as a quantum amplifier. Again, I told you that we have this enhancement of transverse magnetic field because of the coupling with the hyperfine between the nuclear and the electronic spin. So the nuclear spin itself will see a much enhanced transverse magnetic field, and this can be used to detect better a rotating magnetic field. Or if you want, if the diamond itself is rotating with respect to a static magnetic field, the nuclear spin will see a much larger rotation than the electronic spin itself. So what we can do is then to exploit this fact to have an enhancement in the sensitivity to rotation sensing. So as you can see, the rotation of the diamond is very slow, but the nuclear spin see a much larger change, and its dynamics can just be still like adiabatic following of its initial state. So it's very robust to additional noise, but it can give you a very sharp advantage in the sensitivity. So what I show you that we can use the electronic spin both as a quantum mixer, as a quantum controller, and as a quantum amplifier. So all type of quantum advantage that we can get from our quantum sensor without really needing to go for very large quantum entanglement. So this tells us that indeed we can already get some quantum advantages, although of a slightly different time, for hopefully near-term technology. So even beyond the Heisenberg limit, even if we have a small amount of entanglement or some additional degrees of freedom, we can make quantum enhanced sensing much more practical. So for example, we can have a frequency up conversion of this coherence protection or amplification of some external perturbation. So what are other challenges of opportunity for quantum sensor? I think that what Prima described in the previous talks was perfectly spot on. What we want to do is really to try to bring all these devices from our labs out in the world, and there is still a lot of work to be done there. In particular, in trying to make sensors which are much more robust so that they can work in the condition that people are really interested in. And I think the other thing which is quite interesting nowadays is to try to integrate quantum sensor in the larger quantum ecosystem. So really integrate a quantum sensor into quantum networks, integrate quantum sensor with quantum computers so that you can really both exploit, for example, distributed sensing, and also try to use a small quantum computation to improve the sensing task itself. With this, I want to thank the people who have done the work, in particular Minty and Goxin Wang, who's not in this picture because he already graduated. And thank you for your attention. I'm happy to answer some questions.
Okay, so Dr. Marco Quadrilli is taking over. One second, sorry, this is very sensitive. You can take it. Yeah.
Okay.
Can
you hear us? Do you have any questions for Professor Cappellaro?
Any question? We are we can answer there are some questions in the Q&A, but maybe if Professor Cappellaro can answer those offline.
Yes.
Because we are a bit
behind. Okay.
And we can start.
Okay.
Thank you so much.
Thank you so much.
Thank you.
I'll stop my sharing. Thank you again.
Okay.